Good day and welcome back. We'll talk about diffraction. So this is not a new thing for you. We'll learn about the diffraction pattern and also the resolving power of an aperture in this video. So before that, let's look through again the interference phenomenon. We have learned about the condition to have either constructive or destructive interference. The wave which emit from two slits will superimpose and produce interference pattern on the screen. The different things between interference and diffraction is the number of slits involved beside the pattern produced on the screen. So based on Huygen principle, we also have few points at that one slit act as secondary point sources to produce secondary spherical wavelets. The new thing is that the waveform will be bent around the corner of the slit. Let's observe this diagram. For diffraction phenomenon, we'll focus on the distance between the central maximum and the first order minimum or the first dark fringe. We'll divide the slit into half. To produce the first dark fringe on the screen, the optical path difference between the 2 points should be equal to half of the wavelength. From the triangle here, which is similar to what we have discussed in the last video about interference, we also can build the equation that sin theta equal to lambda over 2 divided by a over 2. In the end, we can obtain the equation of sin theta equal to lambda over a. So if we track back on what we have learned before, we also can do the similar approximation that sin theta also equal to x over d, where the x here is the distance between the central maximum and the first dark fringe. And this is different with the formula for the interference pattern. So I repeat again, the formula for the interference and diffraction pattern looks the same, just the variable x is representing different kind of distance. So diffraction phenomenon is the spreading of wave after passing through a slit. The angle here is the diffraction angle from the center to the first minimum, which is showing how great is the effect of the wave spreading. As what you have learned in SPM, the longer the wavelength or the smaller the slit, the wider the spreading effect, which gives us bigger diffraction angle. Let's try one question from the trial paper of SMK King George in 2021. A beam of a laser of wavelength 635 nanometer is directed to a single slit of width 0.05 mm. The pattern formed on the screen placed 1.5 meter from the slit as shown in the diagram. So the diagram is quite interesting that it shows you the waveform of path 1, 2, 3, and 4. In short, the waveform 1 and 2 is showing constructive interference which produce the central maximum, while waveform 3 and 4 are having destructive interference, and this is where the first dark fringe is obtained. So now, we use the formula that we have learned. First thing is to determine the value of x, which is the distance from the central maximum to the first dark fringe. Every information is here. Just substitute in the value in SI unit, you should be able to get the answer 0.019 meter. The next thing that we can expect is to determine the angle of diffraction. So here you can apply sin theta equal to lambda over a. Put in the values, you should be able to obtain the angle is 0.0127 radian. So here you can see that sin theta is approximating to the value of theta in radian form. Approximation of angle is only valid when the angle is very small. We continue with the resolving power of an aperture. It is defined as the ability to distinguish between two objects that are close to each other. The best scenario is that when we look at the sky during the night time, compared to our naked eye, telescope allows us to see a lot more stars, and this is explained by the diffraction phenomenon and the resolving power. Our pupil acts as the aperture, which has lower resolving power than the lens of telescope. For stars that are close to each other and very far from us, we're only able to see as one star or maybe just a blurry two star, just like this image. This happens because of the low resolving power of our eye. Based on Rayleigh criterion, for the image just enough to be resolved, the central maximum of one image falls on the first minimum of the other image. Let's see the example of this image. The value of angle that produces this kind of image is the resolving power of that aperture. It is the minimum angle required, which can be expressed as the ratio of the wavelength and the size of slit, also known as aperture in this case. So different aperture has different resolving power, which is determined by the wavelength or the size of our aperture. So since the wavelength of the light is a constant variable, the resolving power of our human eye is limited by the size of our pupil. So we cannot really see the star as good as the telescope that has better resolving power or smaller value of the minimum angle. So we describe the aperture has a better resolving power when it has the lower value of the minimum angle. For circular aperture like our pupil, we will have a constant value of 1.22 in the equation. Also, we have another similar formula here. If you are given with the distance between that two objects and the distance between the aperture and the screen, We also can express the resolving power as the ratio of X and D. So that's all for my discussion today. If you still have any question, leave it in the comment section below. Also, please do leave a like and subscribe to my channel. I will see you in my next video. Thank you.